Please subscribe to support the channel. Was the Big Bang actually a white hole? That's the kind of question that makes the mind stretch, forcing us to step beyond what we know and peer into the borderlands where science and philosophy meet. When we look at the night sky, we often feel like passive observers of an ancient story written in starlight. But hidden in those distant points of light is the echo of an event so powerful, so incomprehensible, that it gave birth to everything we see. The Big Bang is the cornerstone of modern cosmology, the theory that explains the very beginning of space, time, matter, and energy. And yet, as certain physicists and cosmologists have wondered, what if this cosmic birth wasn't just a unique, mysterious event, but the manifestation of something predicted by the very equations of physics, a white hole? A cosmic mirror to the black holes we now know populate our universe? This question isn't just an exercise in speculation. It strikes at the heart of our deepest mysteries. Was the universe born in a singular eruption that has no precedent? Or could it be part of a larger framework, an elegant symmetry of nature? Could the Big Bang be understood as a white hole, spewing forth everything that exists? Such an idea challenges us to rethink what we mean by beginnings, by causality, and even by the direction of time itself. The beauty of this mystery is that it brings together the known and the unknown. We know the Big Bang happened, our universe is expanding, and the cosmic microwave background radiation is the faint afterglow of its earliest fire. We know black holes exist, gravitational monsters that trap light itself. And we know that Einstein's equations allow for theoretical twins of black holes, white holes. What we don't know is whether the Big Bang could, in some profound sense, be the one and only example of such an object. So we arrive at the central question. Was the Big Bang itself the first, and perhaps the only, white hole? That is the mystery we are about to explore in depth. Now, before we can understand how the Big Bang might connect to the concept of a white hole, we must first lay the groundwork by defining exactly what the Big Bang theory is. The Big Bang is not an explosion in space, as is often mistakenly thought. Instead, it is an expansion of space itself. About 13.8 billion years ago, the universe was condensed into an unimaginably hot and dense state, a singularity where our current laws of physics break down. At that moment, space itself began to stretch, carrying with it matter, energy, and eventually giving rise to galaxies, stars, and planets. One of the most important points to stress here is that the Big Bang did not happen at a single point in space. Rather, it happened everywhere, all at once. Every particle of matter, every photon of light, every quantum of energy began its journey from that initial state. To picture this, imagine inflating a balloon. Every point on the balloon's surface moves away from every other point as the balloon expands. There is no single center of expansion on the surface. Likewise, in the Big Bang, every point in the universe expanded away from every other point. The Big Bang is also not just a hypothesis. It is supported by multiple pillars of evidence. First, the observed expansion of galaxies, measured by Edwin Hubble and others, shows that the universe is getting larger, with distant galaxies receding from us. Second, the cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson, is a faint glow permeating the cosmos, the cooled remnant of the universe's first light, dating back to when the universe was only about 380,000 years old. Third, the abundance of light elements like hydrogen, helium, and lithium matches the predictions of nucleosynthesis that would have occurred in those first few minutes after the Big Bang. But even with all this evidence, the Big Bang leaves us with unanswered questions. What caused it? What came before it? If before even makes sense when time itself began there. And why did the universe start expanding instead of collapsing? These questions are precisely what lead. Was the Big Bang actually a white hole? That question alone has the power to shake the very foundations of how we think about the universe. It is not a casual curiosity. It is a doorway into one of the most profound scientific mysteries we can ask. For centuries, humanity has looked to the skies for answers about where everything came from. But modern science has only recently given us the tools to start piecing together that story. We know that the Big Bang represents the beginning of our observable universe. We also know that black holes, those cosmic giants that swallow everything in their path, exist in abundance. But lurking in the mathematics of Einstein's general relativity is a strange prediction, the possibility of objects that behave as the exact opposite of black holes. These are called white holes. So, naturally, the question arises, could our universe have been born as one of these white holes? Could the Big Bang itself be interpreted as the ultimate white hole, one single, universe-sized eruption of matter and energy from a singularity that we can never look beyond? This isn't just theoretical playfulness. It gets to the core of whether the cosmos is a one-off accident or part of a grand symmetry written into the laws of physics. The fascination here lies in how this question forces us to stretch our imagination. If the Big Bang were a white hole, then everything we know, the galaxies, the stars, the very atoms in our bodies, was the product of a singular, unavoidable outpouring. It would mean that the cosmic story we are living inside isn't just the history of an expansion, but the legacy of a process as natural, in its own way, as the formation of black holes. To even ask the question is to admit how little we truly understand, and how deeply mysterious the universe remains. The Big Bang Theory is our best attempt to describe the origin and earliest evolution of the universe, and while it is one of the most studied and well-supported frameworks in modern science, it is also one of the most misunderstood. People often imagine the Big Bang as some kind of colossal explosion happening at a particular place in an empty void, sending matter flying outward into pre-existing space. But that picture, while dramatic, is deeply misleading. The truth is far stranger and far more profound. The Big Bang was not an explosion in space, it was the rapid expansion of space itself. To truly understand what scientists mean when they say the universe began with the Big Bang about 13.8 billion years ago, we need to reframe how we think about space, time, and matter. Before this event, there was no space into which an explosion could expand, and no time ticking away in the background. Instead, all of space and all of time as we understand them came into being with the Big Bang. It was the birth of everything, not just matter and energy, but the very stage upon which the cosmic drama plays out. At the very beginning, the universe was compressed into an unimaginably dense and hot state. This is often referred to as a singularity, though that word itself comes with caveats. A singularity is a point at which our equations break down, where densities and temperatures become infinite, and the known laws of physics no longer apply. When we trace the universe back mathematically through the expansion we observe today, we arrive at such a singularity. But most cosmologists believe that what existed was not a literal point of infinite density, but rather a regime in which new physics, likely a theory of quantum gravity we have not yet discovered, would be required to properly describe reality. What we can say with confidence is that roughly 13.8 billion years ago, something extraordinary happened. Space began to expand, carrying with it the energy that would eventually cool and condense into matter. Within the first tiny fraction of a second, far less than the blink of an eye, the universe underwent a period of rapid inflation, ballooning exponentially in size. This inflationary epoch smoothed out the fabric of space, explaining why the universe looks so uniform on the largest scales today, despite being peppered with galaxies and galaxy clusters. After this inflationary period, the universe continued to expand and cool. In the first few minutes, nuclear reactions forged the lightest elements, mostly hydrogen, helium, and trace amounts of lithium, in a process called Big Bang nucleosynthesis. For hundreds of thousands of years, the universe remained a hot plasma of protons, electrons, and photons all scattering off one another. It wasn't until about 380,000 years after the Big Bang that the cosmos cooled enough for electrons to combine with protons to form neutral hydrogen atoms. With that event, called recombination, light was finally able to travel freely through space. That ancient light still surrounds us today, stretched by billions of years of cosmic expansion into the faint microwave radiation we call the cosmic microwave background, or CMB. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson provided one of the most compelling confirmations of the Big Bang theory. They were attempting to measure radio signals and instead stumbled upon a faint, persistent noise that seemed to come equally from every direction in the sky. What they had found was the afterglow of creation itself, the cooled relic radiation from the universe's infancy. Later precision measurements, especially by satellites such as COBE, WMAP, and Planck, revealed tiny fluctuations in the CMB that correspond to the seeds of cosmic structure. These fluctuations eventually grew into galaxies, stars, and planets under the influence of gravity. Another critical piece of evidence supporting the Big Bang model comes from the observed expansion of the universe. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it appears to be receding. This relationship, known as Hubble's law, is exactly what we would expect if the universe were expanding uniformly. The fact that galaxies are receding in all directions suggests that space itself is stretching, not that galaxies are rushing through space from a central explosion point. Every observer, no matter where they are in the universe, would see the same pattern of expansion. In addition to the expansion and the CMB, the relative abundances of light elements provide a third major line of evidence. The proportions of hydrogen, helium, and lithium observed in the universe today match almost perfectly the predictions made by Big Bang nucleosynthesis models. If the universe had started differently, or if conditions in those early moments had been even slightly altered, the chemical makeup of everything we see today would be very different. Despite its strengths, the Big Bang theory leaves us with profound questions. What triggered inflation, and why did it stop? What caused the initial expansion in the first place? Was there anything before the Big Bang, or is that question itself meaningless? Some theorists propose that the universe could have emerged from quantum fluctuations in a vacuum. Others suggest that it might be one cycle in an endless series of expansions and contractions, and still others wonder if it might be the outpouring of matter and energy from a white hole. Here's where the intrigue begins to build. The Big Bang looks, on the surface, like an eruption of energy and matter bursting outward into existence. That description sounds remarkably similar to what physicists imagine a white hole would be like, a region of spacetime where matter and energy can only flow outward, never inward. Both concepts involve a singularity and an explosive release. That parallel has led some thinkers to ask, could these two ideas actually be describing the same thing, seen from different perspectives? But before we get there, it is essential to be precise about what the Big Bang theory does and does not claim. The theory does not tell us why the universe exists, nor does it provide a complete picture of the very first moment, t=0. It describes what happened after that moment, how the universe evolved from an extremely hot, dense state into the cosmos we see today. In that sense, the Big Bang is less about the actual bang and more about the expansion that followed. This leaves the door open to speculative but fascinating questions about whether that initial event might be interpreted as something like a white hole, an idea we will explore in depth. The Big Bang remains the single most powerful explanatory model in cosmology, uniting evidence from astronomy, physics, and mathematics. It gives us a coherent narrative for how the universe evolved from near nothingness to everything. And yet, because it leaves unanswered the question of what triggered it, it remains open to reinterpretation. That is why the possibility of linking it to the concept of a white hole is so tantalizing. Could it be that what we call the beginning of the universe is, in fact, an event already foreshadowed in the equations of Einstein's general relativity? A white hole is one of those strange creatures of theoretical physics that lives more in equations than in the observable universe. If black holes are the ultimate cosmic traps, regions of spacetime where gravity is so strong that nothing, not even light, can escape, then white holes are their mirror opposites. They are regions where matter and energy can only escape, but nothing can ever enter. To visualize this, imagine a cosmic volcano that never stops erupting, spewing out light, particles, and radiation, but is completely impenetrable from the outside. No matter how much force you apply, no matter how much matter you hurl at it, nothing would ever cross its boundary. Everything is destined only to move outward. The idea of a white hole arises directly from the mathematics of general relativity. Einstein's field equations, which describe how spacetime curves in the presence of mass and energy, allow for symmetrical solutions. Black holes emerge as one kind of solution, regions where spacetime collapses inward into a singularity. But when you flip the equations in time, when you imagine running the cosmic movie backwards, you get the mathematical possibility of white holes. Where black holes are formed by collapse, white holes exist as eternal outflows. In simple terms, think of black holes and white holes as time-reversed versions of each other. If a black hole is like a sink that swallows everything, then a white hole is like a fountain that endlessly gushes outward. If a black hole has an event horizon that marks the point of no return for anything that falls in, a white hole's horizon marks the surface from which nothing can fall inward. But this is not just a poetic inversion. The physics implied by a white hole is radically different from our everyday experiences. In our universe, matter tends to clump together due to gravity, pulling things inward. A white hole, however, would be defined by perpetual repulsion. It would spit out matter in an unstoppable stream, an object that is not fed by anything outside itself but instead is continuously disgorging its own contents. What makes white holes so fascinating is how they exist on the edge of possibility. The equations of relativity allow them, but that doesn't mean nature actually realizes them. Unlike black holes, which we have observed through gravitational waves, X-ray emissions, and even direct imaging of their shadows, no white hole has ever been detected. They remain purely hypothetical. Many physicists suspect that even if white holes could theoretically form, they would be unstable. A small disturbance, say, a photon brushing against its event horizon, might be enough to destroy it. That fragility could explain why we haven't seen any. And yet, the symmetry is too elegant to ignore. White holes are part of the full solution set of Einstein's equations, meaning that if black holes exist, their opposites can at least be imagined. In fact, early solutions to the equations, like the maximally extended Schwarzschild geometry, naturally include both a black hole and a white hole, connected through a wormhole-like bridge known as an Einstein-Rosen bridge. In practice, that bridge collapses too quickly to be traversable, but mathematically, it demonstrates that black holes and white holes are two sides of the same coin. Physicists sometimes describe white holes as the ghosts of relativity, lurking in the mathematics but not in the sky. But even as abstractions, they play an important role in forcing us to ask, why does nature choose one solution and not the other? Black holes clearly exist in abundance, produced by the collapse of massive stars and the dynamics of galactic centers. White holes, if they exist, don't form from such processes. So if we were to find one, it would hint at something far more exotic, something connected not to ordinary stellar evolution but to the very foundations of space-time. This is where the connection to the Big Bang becomes irresistible. When we describe the Big Bang, we are talking about a singular event where all matter and energy erupted outward from an initial singularity, without anything flowing inward. That sounds eerily similar to the behavior of a white hole. And so, some scientists ask, what if the only white hole that ever existed was the one that created the universe itself? Could the Big Bang have been the ultimate white hole event? Black holes are among the most extreme objects in the cosmos, and their existence is one of the triumphs of modern astrophysics. They are regions of spacetime where gravity has become so overwhelming that not even light, the fastest thing in the universe, can escape. The defining feature of a black hole is its event horizon, a boundary that acts as a one-way gate. Once something crosses this horizon, whether it is a particle, a planet, or even a beam of light, it is doomed to move inexorably inward toward the singularity at the black hole's center. At that singularity, at least as classical general relativity describes it, all matter is crushed into a point of infinite density where our current laws of physics break down. Black holes are not just theoretical curiosities, they are real, and we have abundant evidence of their presence. We have observed stars orbiting invisible companions in ways that reveal enormous unseen masses. We have detected the X-rays emitted by matter heated to extreme temperatures as it spirals into a black hole's accretion disk. We have recorded the ripples in spacetime, gravitational waves, produced when two black holes collide and merge. And perhaps most dramatically, we now have direct images, taken by the Event Horizon Telescope, of the shadow cast by the event horizon of a supermassive black hole at the center of galaxy M87, as well as our own Milky Way Sagittarius A star. These observations make black holes not just theoretical predictions but concrete astrophysical realities. Now, if a black hole is nature's ultimate sink, a cosmic prison from which nothing escapes, then a white hole would be its perfect mirror opposite. A white hole would also have an event horizon, but this horizon would serve the reverse function. Instead of being a point of no return for matter falling in, it would be an impenetrable barrier preventing anything from ever entering. In other words, while a black hole traps everything, a white hole rejects everything. Matter and radiation could pour outward from its horizon, but no force in the universe could push anything back in. The contrast is stark. Picture a black hole as a celestial drain, pulling space-time and everything in it down into a singularity. Now imagine reversing the film reel. Instead of things falling inward, everything rushes outward from a central point, and the horizon becomes a one-way surface in the opposite direction. That is the essence of a white hole. The differences between the two run deeper than simple in and out behavior. Black holes form naturally in our universe when massive stars collapse at the end of their lives, squeezing their cores past the threshold where even light cannot escape. Supermassive black holes appear to form through the growth and merging of smaller ones, anchoring galaxies across the cosmos. White holes, on the other hand, have no known mechanism for formation within our universe. If they exist, they must be born under very different conditions, possibly tied to the fabric of spacetime itself rather than the death of stars. There is also a contrast in their relationship with time. A black hole represents an irreversible process. Once you pass its event horizon, your fate is sealed, and the flow of time pulls you inward toward the singularity. A white hole, by contrast, represents the time-reverse solution to the same equations. It is as though the universe pressed the rewind button on a black hole's life, turning collapse into explosion, ingestion into emission. In that sense, white holes exist more in theory than in practice, as they embody the symmetry of Einstein's equations rather than the physical processes we observe. And yet, by juxtaposing black holes and white holes, we can appreciate the strange beauty of the mathematics that governs our cosmos. They are mirror images. One devours, the other ejects. One marks an endpoint, a cosmic graveyard where information disappears, while the other suggests a beginning, a cosmic fountainhead from which information springs forth. This symmetry is precisely why some thinkers wonder whether the very beginning of our universe, the Big Bang itself, might best be understood as the ultimate white hole, the one grand exception that does exist in reality. The comparison between the Big Bang and a white hole emerges almost naturally once you consider their most striking similarity. Both describe an unstoppable outward eruption of energy and matter. On the one hand, the Big Bang is the story of our universe's birth, a singular event about 13.8 billion years ago when space itself began to expand, carrying with it all the matter, energy, and physical laws we observe today. On the other hand, a white hole, though purely theoretical, is defined as an object from which matter and energy pour outward endlessly, with nothing ever entering in. Both phenomena paint a picture of expansion, of outflow, of something emerging where before there was nothing accessible. When we describe the Big Bang, we talk about a singularity, an initial state of near-infinite density and temperature that marks the boundary of our scientific understanding. When physicists describe white holes, they also invoke a singularity, but one that spews material out into the surrounding universe. It's not difficult to see why some scientists and philosophers of science began asking the question, could these two singularities actually be one and the same? Could what we call the Big Bang be interpreted as the grandest white hole of all, the one that birthed an entire cosmos instead of merely scattering material into an existing universe? The reasoning deepens when we think about time. A black hole is the collapse of matter into a singularity. If you take that process and reverse it, you don't get an implosion, you get an explosion. You get something that looks very much like the Big Bang, matter rushing outward from a singular state. White holes are precisely this kind of time-reversed black hole, predicted by the same equations that gave us black holes in the first place. And so, in that sense, the Big Bang could be seen as the natural time-reversed counterpart to the gravitational collapse that makes a black hole. There is also the sheer scale of the Big Bang to consider. While white holes, as mathematical constructs, are typically imagined as localized objects, mirror twins of black holes, what the Big Bang represents is a universal scale outflow. It wasn't just matter erupting in one location, but everywhere, all at once, as the very fabric of space expanded. If a white hole could exist on a cosmic scale rather than a localized one, it would look very much like what we describe as the Big Bang. Another reason for the comparison lies in the physics of energy release. The Big Bang unleashed a torrent of energy that eventually cooled into the matter and radiation we observe today. Similarly, a white hole is defined by the impossibility of holding onto anything. Energy and matter must flow out. The sheer violence of that process, in both scenarios, is staggering. In both cases, you have a sudden appearance of something from a state that defies conventional explanation, a fountain of existence erupting into reality. It is also worth noting that the comparison appeals to our desire for symmetry and elegance in the laws of nature. Black holes exist in abundance, proven by observation. Their mirror image solutions, the white holes, remain hypothetical. But if the universe itself began in a way that mirrors what a white hole would do, then perhaps we have already encountered a white hole without realizing it. Perhaps we live inside its eruption. The idea is not mainstream, but it is compelling precisely because it ties together two seemingly separate phenomena, cosmic birth and cosmic collapse, into a single, unified picture. And beyond the mathematics, the comparison sparks a deeper philosophical curiosity. If black holes are the endpoints of matter, the cosmic places where information is swallowed up, could white holes represent beginnings, places where information and matter emerge? If so, then perhaps the greatest white hole of all is the one that gave rise to the universe itself. In that sense, the Big Bang isn't just like a white hole. It may be the only white hole that ever existed, a one-time eruption that birthed everything we know. Time symmetry is one of the most fascinating and subtle aspects of Einstein's general theory of relativity, and it lies at the heart of the discussion about whether the Big Bang could be thought of as a white hole. To understand this idea, we must first remember that general relativity doesn't dictate a single unique outcome for the universe. Instead, it provides a set of equations, Einstein's field equations, that describe how mass, energy, and spacetime interact. These equations are surprisingly flexible, admitting multiple possible solutions depending on the boundary conditions and assumptions we feed into them. One of the striking properties of Einstein's equations is that they are time-symmetric. This means that if you take a valid solution that describes a physical scenario evolving forward in time and then flip the time coordinate, effectively running the film backward, you get another valid solution. In the same way that Newton's laws of motion or Maxwell's equations of electromagnetism don't inherently prefer one direction of time over the other. General relativity also treats time neutrally at the level of pure mathematics. This is where black holes and white holes come into play. A black hole is a solution that describes the gravitational collapse of matter, forming a region of spacetime from which nothing can escape. Now, if you take that solution and reverse the arrow of time, what do you get? You don't get a collapsing object. You get an expanding one. You get a white hole, a region of spacetime into which nothing can enter, and from which matter and energy are expelled outward. In other words, white holes are not something physicists invented out of imagination. They emerge naturally as the time-reverse counterpart of black holes within Einstein's framework. To picture this, imagine a black hole as a one-way tunnel through spacetime. On the way in, everything falls through the event horizon, trapped forever. But if you reverse time, you see the opposite process. Instead of matter being swallowed, matter is expelled. The event horizon is still a one-way gate, but now it only permits outward motion. This is the essence of the time symmetry idea. Two sides of the same mathematical coin, one moving forward in time, the other backward. The Schwarzschild solution, which was the very first exact solution to Einstein's equations discovered in 1916, illustrates this perfectly. When you fully extend this solution mathematically, you don't just get a black hole. You also get a white hole region, connected to the black hole by a wormhole-like structure known as an Einstein-Rosen bridge. In theory, this means that the complete geometry of a non-rotating, uncharged black hole actually contains both a black hole and a white hole, though the white hole portion is generally considered unphysical because it doesn't seem to arise from any realistic process in our universe. And yet, the mere fact that the mathematics allows such solutions is profound. It means that relativity itself doesn't forbid white holes. Instead, it presents them as mirror image possibilities that exist alongside black holes in the space of solutions. If nature has chosen to realize black holes, is it unreasonable to wonder whether it might also realize white holes in some form? Perhaps not as isolated objects floating in space, but maybe as something more fundamental, something like the Big Bang itself. The time symmetry perspective also forces us to confront the difference between the timeless beauty of mathematics and the messy reality of physics. In practice, our universe doesn't appear perfectly time-symmetric. Processes like entropy, the increase of disorder, give time a clear direction, the arrow of time we experience. Black holes form naturally from stellar collapse, but white holes don't seem to form spontaneously in the same way. This suggests that while relativity permits white holes on paper, the actual physics of our universe might prevent them from manifesting, except, perhaps, in the one-off event we call the Big Bang. From this standpoint, comparing the Big Bang to a white hole is not a random stretch of imagination but a logical extension of time symmetry. If black holes represent the end state of matter collapsing inward, then white holes represent a beginning state of matter erupting outward. And if we think of the universe as having a beginning, an eruption of space and time itself, then it makes sense to ask, was that beginning simply the manifestation of a white hole on the largest possible scale? Unlike black holes, which have moved from theoretical prediction to firmly established astrophysical reality, white holes remain purely speculative. They are mathematical possibilities suggested by Einstein's equations, but so far, nature has given us no evidence that such objects exist in the observable universe. This difference between prediction and observation is crucial, because while physics often begins with mathematical solutions, it only earns its place in reality through evidence. Black holes made the journey from theory to observation in a dramatic way. When Einstein's general relativity was first published in 1915, the equations almost immediately hinted at the existence of regions where gravity could trap light. Carl Schwarzschild, solving the equations only months later, produced the first black hole solution. For decades, though, the idea remained an oddity, debated and sometimes dismissed by physicists who thought such extreme objects might not exist in nature. But as astronomical technology improved, we found compelling signs of their presence. We detected stars orbiting invisible masses, gas heated to millions of degrees as it spiraled inward, gravitational waves from mergers, and finally direct imaging of black hole shadows. Today, black holes are no longer exotic speculations, they are observable features of the cosmos. White holes, in contrast, have never made this leap. No telescope, no detector, no instrument has ever found anything behaving like a white hole. No region of space has ever been observed continuously ejecting matter and radiation while remaining completely impervious to anything entering. And unlike black holes, which can naturally form from collapsing stars, there is no known process in astrophysics that would create a white hole. That lack of a formation mechanism makes them seem more like mathematical ghosts than physical objects. Physicists also suspect that even if a white hole could exist, it would be violently unstable. A single photon, a single speck of matter approaching its horizon, could disrupt the entire solution. This instability implies that white holes, if they ever did exist, would collapse or evaporate almost instantly, leaving no trace. This fragility contrasts sharply with black holes, which can persist for billions of years. Yet, the absence of observational evidence doesn't entirely erase white holes from the conversation. Their existence is not forbidden by the mathematics of general relativity. They are consistent, valid solutions of Einstein's equations, and this keeps them alive as theoretical possibilities. Some researchers treat them as useful tools for exploring time symmetry, the information paradox, and even quantum gravity. Others speculate that while white holes may not exist as local astrophysical objects, they might appear in extreme, universe-wide contexts, such as the Big Bang. This is why the idea of comparing the Big Bang to a white hole has gained traction in certain circles. Since white holes have never been observed directly, it is possible that they cannot exist in the way black holes do, as individual cosmic objects. But if there were only one white hole, the ultimate white hole, it might be the Big Bang itself. In this view, the lack of evidence for white holes elsewhere isn't a problem. It's a feature, there was only ever meant to be one, and that one gave birth to everything. When cosmologists trace the history of the universe backward through time, they arrive at a startling conclusion. Everything we see today, every galaxy, every star, every planet, every atom, was once compressed into a state of unimaginable density and temperature. In the language of physics, this initial condition is called a singularity. A singularity is not just a really dense point in space. It is a place where the known laws of physics, as we currently understand them, break down completely. Our equations yield infinities: infinite curvature of space-time, infinite density of matter, infinite temperature. These infinities aren't physical objects we could point to, they are signals that our models no longer apply, that we have entered a domain where a deeper theory is required. The Big Bang singularity is often compared to the singularity at the center of a black hole. In both cases, general relativity predicts a point where space-time is so warped that conventional descriptions fail. In a black hole, all the matter that falls inside the event horizon is inexorably pulled toward the center, where it collapses into a singularity. At that point, densities rise without bound, and time itself seems to come to an end. Similarly, when we project the universe's expansion backward in time, the density of matter and energy approaches infinity at the moment of the Big Bang, suggesting another singularity. But there are crucial differences. The singularity inside a black hole is hidden behind an event horizon. No information from it can ever reach us, which is why it is often described as cloaked from view. In contrast, the Big Bang singularity is not hidden. It is not a point buried deep inside spacetime. It is the origin of spacetime itself. Every point in the universe was once part of that singularity. This means the Big Bang singularity is not over there in some distant location. It is everywhere. Every galaxy, every atom, every cubic centimeter of space was once contained within that primordial state. The similarity between the two singularities, however, raises intriguing questions. If black holes and the Big Bang both feature singularities, could they be related? Could the physics that governs one help explain the other? This is part of why some theorists wonder if the Big Bang could be interpreted as a kind of white hole. Both involve singularities, but one represents an inward collapse, while the other represents an outward eruption. Yet, we must be cautious. The singularity at the Big Bang is not something we have observed directly. It is an extrapolation of our mathematical models. The universe we can study, the cosmic microwave background, the distribution of galaxies, the abundance of elements, tells us a great deal about conditions a fraction of a second after the Big Bang. But the singularity itself, that point of infinite density and temperature, lies beyond the reach of our current theories. It is a boundary where relativity alone cannot guide us. To understand it fully, we will need a theory of quantum gravity, one that merges Einstein's description of spacetime with the probabilistic framework of quantum mechanics. Still, the analogy between black hole singularities and the Big Bang singularity is powerful. Both suggest extreme states where time and space as we know them lose their meaning. Both challenge the limits of human understanding. And both hint that singularities may not be points in the traditional sense, but doorways into new realms of physics. So when we say the Big Bang was a singularity, we are saying that it shares something fundamental with the singularities at the hearts of black holes. They are the places where our equations stop working, where infinities appear, and where new physics is demanded. The mystery is whether these two kinds of singularities, one hidden, one universal, are manifestations of the same deeper truth. If so, then perhaps the Big Bang was not just a singularity, but the singularity, the one that erupted instead of collapsed, the one that gave us not an end but a beginning. Einstein's general theory of relativity, published in 1915, is the foundation of our modern understanding of gravity. Instead of treating gravity as an invisible force pulling on masses, relativity describes it as the curvature of spacetime itself. Matter and energy tell spacetime how to curve, and spacetime tells matter how to move. Out of this deceptively simple principle come equations, the Einstein field equations, that are both elegant and brutally difficult. Solving them under different conditions produces different possible universes, different cosmic objects, and sometimes, results that seem almost fantastical. One of the remarkable aspects of these equations is that they do not forbid the existence of white holes. In fact, white holes arise naturally from some of the very same mathematical solutions that describe black holes. The most famous example is the Schwarzschild solution, the first exact solution to Einstein's equations found in 1916. This solution describes a spherically symmetric, non-rotating black hole. But when you extend the mathematics fully, when you explore not just the forward in time case but also its time reverse, you end up with a spacetime that contains not only a black hole but also a white hole. This complete Schwarzschild geometry actually features four regions, two asymptotically flat universes, one connected to a black hole and one to a white hole, with the two singularities linked by a bridge known as an Einstein-Rosen bridge or wormhole. In this mathematical construct, matter could in principle fall into a black hole in one universe and emerge from a white hole in another. It's a stunningly symmetrical vision of space-time. But it also comes with bizarre, almost paradoxical implications. For one, the existence of a white hole region would mean there are places in the universe that constantly emit matter and energy without any apparent source, and into which nothing could ever enter. This breaks our everyday intuition about conservation and stability. How can matter just appear out of nowhere? How can an event horizon prevent entry but allow escape? These are not violations of relativity itself, but they strain our understanding of physical reality. Another strange prediction is that white holes, unlike black holes, would be past singularities rather than future ones. A black hole represents a fate. Once you fall in, you are destined to reach the singularity in the future. A white hole, by contrast, represents a beginning, particles and light streams are emanating outward from a singularity in the past. From the perspective of time symmetry, this makes sense. But from the perspective of astrophysics, it raises a question. Why do we see black holes forming naturally all over the universe, while we see no evidence of white holes? If relativity's equations are symmetric, why isn't nature symmetric in this way too? Some physicists argue that this asymmetry arises from the arrow of time and the role of entropy. The universe favors processes that increase disorder. Black holes, which swallow matter and hide information behind horizons, align with this thermodynamic arrow of time. White holes, which would require matter to spontaneously assemble and emit in a perfectly ordered way, would run against it. This could explain why relativity allows them mathematically but the universe seems not to permit them physically, or at least not in any stable form. Still, the fact that relativity does not forbid white holes is important. It means we can take them seriously as theoretical constructs. They appear as legitimate solutions, not as mistakes or mathematical flukes. And because they emerge naturally in the same framework that gave us black holes, objects we now know exist in abundance, we cannot dismiss them entirely. Instead, we must ask, if the universe does not manifest white holes as localized objects, could it manifest them in some other way? Could the one exception to the rule be the greatest singularity of all, the Big Bang itself? In this sense, Einstein's equations leave the door open. They tell us that white holes are possible but strange. They predict behaviors that defy our everyday intuition and challenge the stability of physical processes. Yet, by allowing them, they also give us a tool for thinking about beginnings as well as endings. Where a black hole singularity represents a collapse into the future, a white hole singularity represents an eruption from the past. And when we think about the universe's birth, that description feels uncomfortably close to home. When cosmologists describe the Big Bang, one of the most defining features they emphasize is its colossal release of energy. In an instant, the universe went from an incredibly compact, unimaginably hot state to a rapidly expanding cosmos filled with radiation and particles. That initial release wasn't a gentle trickle, it was an eruption of staggering intensity. Every photon of light, every particle of matter, every quantum of energy we observe today was once packed into that prime-val fireball. This explosive beginning is why the analogy to a white hole feels so compelling. By definition, a white hole is an object that continuously ejects matter and energy into its surroundings, without ever letting anything back in. The Big Bang, too, was an outpouring event, an unstoppable expansion of energy into what became space and time. While the Big Bang was not an explosion in space but an expansion of space itself, the visual parallel is undeniable. Both involve matter and energy moving only outward, never inward, driven by conditions so extreme that they escape ordinary physical descriptions. Consider the sheer scale of this energy outflow. Within the first trillionth of a second, the universe expanded exponentially during what physicists call cosmic inflation. This brief epoch saw the universe grow from smaller than a subatomic particle to something macroscopic, far larger than our solar system, in less than a blink. In that fleeting moment, enormous amounts of energy were released, smoothing out space and seeding the tiny fluctuations that would later grow into galaxies and stars. That burst of inflationary energy mirrors the fundamental idea of a white hole. Matter and radiation spilling out from a singularity, unidirectionally, unstoppable. After inflation, the universe continued to radiate energy. In the first few minutes, nuclear fusion occurred on a cosmic scale, producing the light elements hydrogen, helium, and lithium. Then, for hundreds of thousands of years, the universe was filled with a dense, hot plasma that radiated photons constantly. When it cooled enough for atoms to form, light was finally able to travel freely. The afterglow of that energy outflow is still visible today as the cosmic microwave background radiation. It is, in a sense, the fossil evidence of the universe's great release, the echo of an event very much like what a white hole would have produced. The resemblance becomes clearer when we compare black holes and the Big Bang side by side. A black hole traps energy forever, nothing escapes. A white hole, in theory, would be the exact opposite, a place where energy cannot be contained, where it is flung outward in all directions. The Big Bang looks exactly like that, a universal scale outflow that has never stopped. In fact, you could say we are still living inside that outflow today, as galaxies continue to drift apart in the ongoing expansion of the universe. But there are important differences. A white hole, as normally conceived, is imagined as a localized object, a kind of mirror twin to a black hole. The Big Bang was not local. It didn't spew matter into a pre-existing space. It was the creation of space itself. Instead of an object ejecting energy into its environment, it was the emergence of the environment itself, with energy embedded in it from the start. Still, on the level of raw description, an unstoppable outpouring of matter and energy with no return, the similarities are striking. This is why many theorists entertain the possibility that the Big Bang might be the only white hole that has ever existed. If a white hole on a cosmic scale were possible, it would look almost exactly like what we call the Big Bang, a one-time eruption that marked the beginning of everything, rather than a repeating astrophysical process. The continuous outflow of energy we see in the universe's expansion could then be viewed not as a separate phenomenon, but as the natural signature of that primordial white hole. Of course, there are deep mysteries still unsolved. Where did the energy of the Big Bang come from? Was it released from some previous state, or did it emerge from nothing at all? If it was a white hole, does that mean it was connected to a black hole elsewhere, perhaps in another universe? These questions remain open, but the similarity between the energy outflow of the Big Bang and the theoretical behavior of a white hole is more than coincidence. It hints at a symmetry hidden within the laws of physics, one that might connect the end states of black holes to the beginning state of the cosmos itself. Could it be that the Big Bang was not simply the beginning of our universe, but the only white hole that has ever existed? This question sits at the heart of one of the most fascinating cosmological debates. If we follow Einstein's equations, white holes are mathematically possible. But unlike black holes, which we have observed indirectly through gravitational waves, X-ray emissions, and even the iconic image of their event horizons, white holes have never been detected in nature. No astrophysical body has ever shown the telltale signs of matter and energy constantly pouring outward without a source. So why might that be? One provocative idea is that white holes are not ongoing phenomena at all. They are not stable, lasting objects like stars or galaxies. Instead, a white hole may have happened once, and only once, in the form of the Big Bang itself. In this view, our universe is the product of a single, cosmic-scale white hole event. It was not just another astrophysical oddity, it was the mother of all eruptions, a singular release of everything we now see. This idea reshapes how we think about cosmic beginnings. A black hole is an endpoint, the death of a star or the collapse of matter under its own gravity. If a white hole is truly its time-reversed twin, then it makes sense that it would not be something that repeats or forms naturally within our universe. Instead, it would stand at the absolute beginning, marking the one great transition from nothingness, or from some prior state we cannot yet describe, into existence. In this framing, the Big Bang is not just like a white hole, it is the ultimate white hole, the archetype, the only one that ever mattered. The appeal of this interpretation lies in its simplicity. Rather than asking why we don't see white holes scattered throughout the universe, we could say, they were never meant to exist repeatedly. They were meant to exist once, as the grand opening event of reality itself. The Big Bang's singular outflow of matter and energy would be all the evidence of a white hole that we should ever expect to see. But this interpretation also forces us to ask difficult questions. If the Big Bang was a white hole, where was it attached? Was it the outflow from a black hole in some other universe, spewing its contents into what became ours? If so, then our one-time white hole may actually be part of a grander cosmic chain, with universes giving birth to one another through black hole-white hole transitions. Alternatively, if the Big Bang was a white hole without a parent black hole, then it was truly unique, a singular event that stands outside of all known processes. That would suggest that our universe is not one link in a cosmic cycle but rather a one-of-a-kind occurrence, without precedent and without repeat. The notion of the Big Bang as a one-time white hole also brushes up against philosophy. If this was the only white hole, was it inevitable? Did the laws of physics demand it? Or was it a contingent event that might never have happened? When we ask whether the Big Bang was the only white hole, we are really probing whether the birth of our universe was a cosmic accident or a necessity written into the very structure of reality. Another angle to consider is the arrow of time. White holes, if they exist, would represent the past boundary of time. events where everything flows outward from a singularity, never backward in. That description fits the Big Bang perfectly. It was not only a physical eruption, it was the moment when time itself began to flow. If time has a single origin, then the white hole that started it all must also be a one-time occurrence. There could not be multiple beginnings, multiple arrows, without splintering reality into entirely disconnected universes. And yet, the possibility remains that our one-time white hole may not be unique across all of existence. If the multiverse idea is correct, then countless other universes may have had their own white hole-like beginnings. In that case, our Big Bang would be one among many, but still unique within our own cosmic domain. We would live in a universe where white holes are not repeatable phenomena inside the cosmos, but rather the very act of a cosmos coming into being. The profound mystery is that we have no way, at present, to test whether the Big Bang was the only white hole. We cannot look beyond the earliest fractions of a second, and we cannot observe anything outside our own cosmic horizon. But the hypothesis that the Big Bang was the universe's one-time white hole remains a hauntingly elegant way to think about why we see no others. It answers the question of their absence by elevating the Big Bang into the one cosmic eruption that needed no precedent and admits no repeat. Entropy and the arrow of time are at the heart of why the universe looks the way it does, and they give us a powerful lens through which to examine the Big Bang and its possible connection to white holes. To begin, entropy is a measure of disorder, or more precisely, the number of possible microscopic configurations that correspond to a macroscopic state. In everyday terms, it's the reason why an egg breaks when it falls but never spontaneously reassembles, why perfume disperses through a room instead of reconcentrating back into the bottle, and why we grow older rather than younger. This forward flow of time, the arrow that gives events a clear direction from past to future, is deeply tied to entropy. According to the second law of thermodynamics, in any closed system, entropy tends to increase. Our universe is the ultimate closed system, and so as time progresses, it inexorably evolves towards states of greater disorder. Now, how does this relate to black holes and white holes? Let's start with black holes. A black hole swallows matter and energy irreversibly. Once something crosses the event horizon, it cannot come back out. From the perspective of entropy, this is a one-way street. In fact, Stephen Hawking showed that black holes are not just gravitational prisons, they have entropy themselves, proportional to the area of their event horizons. As a black hole absorbs matter, its entropy grows, perfectly consistent with the universal rule that disorder must increase. Time moves forward, entropy rises, and black holes are the ultimate entropy engines. White holes, by contrast, flip this picture. If a white hole were real, it would not absorb matter, it would only eject it. Everything inside would be pushed outward, and nothing could ever enter. From the standpoint of entropy, this seems odd. To generate a white hole, matter would have to come streaming outward in a highly ordered way, almost as if the universe were running backward in time. A white hole, then, appears to represent the time reverse of a black hole. Where black holes mark the inexorable pull toward the future, white holes seem to point back toward the past. This brings us to the Big Bang. At the universe's birth, time itself began, and it began pointing in one direction, forward. From a state of extraordinarily low entropy, an initial condition of remarkable smoothness and order, the cosmos erupted outward. As it expanded, entropy increased. Particles diffused, stars formed and burned, galaxies swirled into complex structures, and disorder grew. In other words, the Big Bang set the arrow of time in motion, just as a white hole would. The universe began as a low entropy state and has been marching toward higher entropy ever since. But here lies one of the great mysteries of cosmology. Why was the entropy of the early universe so low in the first place? If the Big Bang was a kind of white hole, then its role was not only to eject energy and matter outward but also to define the very direction of time. In this sense, the Big Bang as white hole interpretation fits naturally. It explains why we don't see entropy running backward, why we never witness broken eggs reassembling or heat flowing from cold to hot. The Big Bang, as the one-time white hole, fixed the arrow of time at the very beginning. Black holes, on the other hand, represent the opposite end of this cosmic journey. They are entropy sinks, swallowing complexity and turning it into horizon area. If the Big Bang was a white hole, then the story of the universe becomes almost poetic. It begins with a single white hole of incredibly low entropy and may end with countless black holes, each maximizing entropy in their own domains. Time, in this sense, is the bridge between them. Some theorists even speculate that this interplay between black holes, white holes, and entropy could resolve deep puzzles like the information paradox. If information lost in a black hole was somehow expelled through a white hole, perhaps in another region of space-time, it would preserve the ultimate balance of entropy while still giving time its irreversible direction. Ultimately, the arrow of time is what makes the comparison between the Big Bang and a white hole so powerful. A white hole is, in essence, a time-reversed black hole. The Big Bang, too, looks like the reverse of gravitational collapse, a singularity not of endings but of beginnings, where time points outward and forward forever. In this light, entropy doesn't just describe disorder, it tells the story of the universe itself. The Big Bang marked the birth of time's arrow, the launching point of entropy's unending rise, and the one event where a white hole analogy may capture not just the physics but the very essence of why reality unfolds the way it does. When we talk about the possibility of white holes and their connection to the Big Bang, we eventually run into one of the deepest, most stubborn problems in all of physics: the incompatibility between quantum mechanics and general relativity. On their own, these two great frameworks of science work remarkably well. General relativity, Einstein's masterpiece, describes gravity as the curvature of space-time, governing planets, stars, galaxies, and the cosmos at large. Quantum mechanics, on the other hand, governs the microscopic realm of atoms, particles, and the strange probabilistic behavior of matter and energy on the smallest scales. Each is powerful, predictive, and experimentally verified. Yet when we try to make them talk to each other in extreme situations, like black holes, white holes, or the Big Bang, they clash. White holes sit squarely in that clash. General relativity, at least in its mathematical form, permits them. If you take the equations describing a black hole and reverse the direction of time, you get a white hole solution. The math doesn't forbid them. But when you introduce quantum mechanics into the picture, strange things happen. White holes, unlike black holes, seem unstable. Tiny fluctuations in quantum fields could destabilize them instantly, causing them to collapse or vanish before they could even form. This is one reason why white holes are still considered speculative. While relativity says they could exist, quantum theory whispers that nature probably doesn't allow them to survive. This same problem emerges when we try to describe the Big Bang. The standard Big Bang model works very well from the moment the universe was about a fraction of a second old, when the laws of physics we understand can be applied to describe expansion, cooling, and the formation of particles. But if we roll the clock further back, to the very first instant, the singularity itself, our equations break down. General relativity predicts infinite density and curvature, a true singularity. Quantum mechanics, however, tells us that infinities should not be physically real. At the smallest scales, uncertainty and quantum fluctuations dominate, smoothing out such extremes. Without a theory of quantum gravity, one that unites these two pillars, we cannot say exactly what happened at time zero, nor can we say with certainty whether the Big Bang could really be a white hole. Some candidates for quantum gravity, like loop quantum gravity or string theory, have proposed fascinating scenarios that connect directly to our question. In loop quantum gravity, for example, a collapsing black hole might undergo a bounce, avoiding a singularity and re-expanding as a white hole. That bounce could even spawn a new universe on the other side of the black hole horizon, which would look to its inhabitants like a Big Bang. String theory, with its extra dimensions and brands, also allows for Big Bang-like events that emerge from deeper structures of reality. But all of these remain hypotheses. We lack experimental evidence. The uncertainty surrounding white holes reflects a broader truth. We simply do not know what spacetime is really made of at the smallest scales. General relativity treats it as smooth and continuous, like a fabric that can be bent and curved. Quantum theory suggests it may be granular, full of fluctuations and foamy structures. Without understanding this microscopic texture of spacetime, we cannot say whether the equations that allow white holes are real features of the universe or just mathematical curiosities. This is why white holes remain in the realm of speculation. They may be possible solutions in Einstein's equations, but until we reconcile those equations with the rules of quantum mechanics, we cannot decide whether white holes could form, persist, or explain our universe's birth. The same holds for the Big Bang itself. Was it truly a singularity, or was it a quantum transition that we do not yet have the tools to describe? Was it a white hole, or something even stranger that only a theory of quantum gravity can reveal? In this sense, white holes act as a kind of beacon for physics. They point us toward the unsolved frontier where gravity and quantum mechanics collide. They highlight the cracks in our current theories and challenge us to unify them. Until we do, white holes, and the possibility that the Big Bang was one, will remain tantalizing ideas, perched at the edge of what science can say with confidence. One of the most fascinating and daring ideas in modern theoretical physics is the possibility that black holes and white holes are not isolated, unrelated entities, but rather two sides of the same cosmic coin. Black holes, as we know, are regions of spacetime where gravity is so extreme that nothing, not even light, can escape. They pull matter and information inward, locking it behind an event horizon. But if we extend Einstein's equations in a time-reversed way, we end up with white holes, objects from which nothing can enter, but everything inside must pour outward. This duality sparks an extraordinary hypothesis. Perhaps what black holes swallow could eventually emerge elsewhere as white holes. This idea takes us directly into the heart of the black hole information paradox. According to quantum mechanics, information about a physical system can never be truly lost. If you know the precise quantum state of something, even if it changes form, that information should still exist in some way. But black holes pose a serious problem. If matter falls into a black hole and the black hole eventually evaporates via Hawking radiation, the outgoing radiation seems to carry no record of what originally fell in. The information appears to be destroyed, a violation of quantum principles. This is the paradox. Now, enter the white hole connection. What if, instead of disappearing forever, the information that black holes swallow is stored or transformed, and then later expelled, not in the same place, but somewhere else, sometime else, through a white hole? In this picture, the universe would conserve information by linking the death throes of black holes to the birth of white holes. Matter and energy go in, but they do not vanish. They re-emerge, possibly in another region of our universe or even in another universe entirely. Some theorists have even proposed that every black hole might eventually bounce. Instead of collapsing to a singularity and evaporating into nothingness, the intense density inside a black hole could trigger quantum gravitational effects that reverse the collapse. This reversal would transform the black hole into a white hole, spewing out the information it once swallowed. If true, black holes would not be final endpoints of matter but rather gateways, portals through which information cycles back into reality. Imagine the implications. A star collapses into a black hole, its matter compressed beyond recognition. Billions or trillions of years later, when quantum gravity effects dominate, that black hole transitions into a white hole, erupting outward. The information encoded in the original star, once thought lost, is released. In this sense, black holes could act like cosmic recycling machines, breaking matter down and later reintroducing it into the universe through white holes. Even more mind-bending is the suggestion that these white holes may not appear in our own universe at all. They could emerge in entirely new universes. A black hole in our cosmos might form the seed of another cosmos on the other side, with its own space, time, and physical laws. To observers inside that new universe, the Big Bang would look like a white hole, matter and energy erupting outward, seemingly from nothing. This connects directly to the idea that our own Big Bang may have been the white hole counterpart of a black hole in some parent universe. Of course, this remains speculative. There are enormous hurdles to the theory. For one, no white holes have been observed. For another, the timescales involved could be so vast, far longer than the current age of the universe, that we may never witness such a transition. Furthermore, many physicists argue that the extreme instability of white holes makes them unlikely to exist, much less act as information outlets. Still, the black hole-white hole connection persists in theoretical research because it is elegant. It offers a potential resolution to the information paradox, preserves the principle of information conservation, and provides a neat symmetry in the fabric of space-time. Instead of seeing black holes as destructive dead ends, we might one day see them as gateways to renewal, their hidden interiors giving birth to white holes somewhere beyond our cosmic horizon. The concept of wormholes, or Einstein-Rosen bridges, adds an entirely new layer of fascination to the discussion of black holes, white holes, and the Big Bang. A wormhole, in the most basic sense, is a hypothetical tunnel through space-time, a shortcut that links two distant regions of the universe, or even two separate universes entirely. Imagine folding a piece of paper so that two distant points touch, then poking a hole through. The line that connects them is the wormhole. In physics, this idea emerges directly from Einstein's theory of general relativity. The specific type of wormhole most relevant to black holes and white holes is the Einstein-Rosen bridge, first proposed by Albert Einstein and his collaborator Nathan Rosen in 1935. When they studied the solutions to Einstein's equations for black holes, they noticed something peculiar. If you extend the mathematical description of a black hole beyond its singularity, you find another solution that looks like a white hole. In this construction, the black hole and white hole are not isolated but connected by a throat or bridge, a wormhole. Matter falling into the black hole could, in principle, re-emerge from the white hole at the other end. At first glance, this seems like the perfect mechanism for solving some of the mysteries we've been exploring. The black hole swallows matter and information, and instead of being lost forever, they pass through the wormhole and burst outward from a white hole elsewhere. This offers a neat symmetry: black holes as cosmic inlets, white holes as outlets, wormholes as the pipes that connect them. But here's the catch: Einstein-Rosen bridges are not stable. According to general relativity, these wormholes pinch off so quickly that nothing, not even light, can pass through them. To keep a wormhole open, some kind of exotic matter with negative energy density would be required, something that has never been observed. Without this exotic stabilizer, the wormhole collapses in on itself almost instantly. In other words, while the equations allow black hole-white hole connections through wormholes, nature may not. Still, the idea refuses to die, because it is so compelling. Wormholes provide a possible answer to the information paradox, a potential escape hatch for matter and energy trapped in black holes, and even a framework for cosmogenesis, the birth of new universes. In some speculative scenarios, a black hole in our universe could be linked via a wormhole to a white hole that is the Big Bang of a different universe. To the beings living inside that new universe, their cosmos would seem to have appeared from nothing, while to us, it would simply be the other side of a bridge. Physicists have pushed this concept further with modern theories. In certain quantum gravity frameworks, wormholes might not just be abstract geometry but could arise naturally at the smallest scales of space-time. The idea of ER equals EPR, proposed by Juan Maldacena and Leonard Susskind, even suggests that wormholes, Einstein-Rosen bridges, and quantum entanglement, EPR pairs, are two faces of the same phenomenon. If true, this would mean that entanglement, the spooky action Einstein himself distrusted, could be the fundamental glue of space-time, literally stitching together black holes and white holes through quantum threads. Of course, the experimental evidence is non-existent. We have never seen a wormhole, let alone traveled through one. For all we know, they may remain forever in the realm of mathematics and science fiction. And yet, they serve as powerful thought experiments. If black holes and white holes are linked by wormholes, then perhaps every collapse in our universe is paired with a creation somewhere else. Perhaps our own Big Bang was not a singularity at all, but the opening of a wormhole throat, a white hole connected to a black hole in a parent cosmos. Wormholes remind us of the strange possibilities that general relativity allows: doorways in space-time, shortcuts through reality, and bridges between universes. Whether or not they exist physically, they provide a framework to imagine how black holes and white holes might be part of a grander cosmic network, one where endings and beginnings are not isolated events but connected chapters of a much larger story. The notion that the Big Bang could itself be the exit point of a white hole is one of the boldest and most mind-expanding ideas in all of cosmology. Instead of picturing our universe as a unique, one-off explosion that happened for no reason, this theory asks us to consider a deeper possibility. What if the Big Bang was not an isolated beginning at all, but the outward eruption of matter and energy from a black hole in another universe? In other words, our cosmos might be the white hole end of a process that began elsewhere. To see why this is intriguing, let's step back. A black hole forms when matter collapses under its own gravity to such an extreme density that it curves space-time into a bottomless pit. At the center lies what relativity predicts as a singularity, a region of infinite density where the laws of physics break down. Traditionally, we think of this as the ultimate dead end. But if we reverse the flow of time in Einstein's equations, that singularity could become the birthplace of a white hole, a region that explodes outward, releasing everything trapped inside. Now imagine that black holes in some parent universe don't just trap matter forever. Instead, when they collapse, they create new universes. From the outside, in the parent cosmos, the black hole looks like a region of no return. But on the inside, from the perspective of the new universe, what emerges looks exactly like a Big Bang, a violent eruption of energy and matter filling an expanding space-time. This would mean that our Big Bang was the white hole counterpart of a black hole in another universe. We are, in essence, living inside the birth cry of another cosmos's collapse. This model has a certain elegance to it. It explains why the Big Bang seemed to come from nothing. From our perspective, the universe began with an outpouring of matter and energy at a singularity. But from the perspective of the larger multiverse, our nothing was simply the other side of an event horizon. It also suggests that the cycle of cosmic creation is continuous. Universes give rise to other universes, each Big Bang seeded by the collapse of a black hole elsewhere. The theory has even been explored in serious physics. In approaches like loop quantum gravity, researchers suggest that singularities may not actually exist. Instead, quantum effects prevent the collapse from reaching infinite density, causing a bounce. The inside of a black hole could rebound into expansion, appearing as a Big Bang to those on the other side. This is sometimes called the black hole bounce model. It elegantly avoids infinities, preserves information, and ties the origin of universes to the natural processes of gravitational collapse. Of course, there are challenges. For one, we have no way of peering outside our universe to see whether it is indeed connected to a parent cosmos. The event horizon of a black hole prevents outside observers from seeing what happens inside, and similarly, our cosmic horizon prevents us from looking beyond the Big Bang. Furthermore, the energy scales involved are so extreme that our current theories, general relativity and quantum mechanics, both break down. Without a fully developed theory of quantum gravity, we cannot rigorously test whether a black hole could give birth to a white hole universe. But the appeal of the idea is undeniable. It suggests that universes may not begin with inexplicable miracles but with natural processes, rooted in the same physics that governs stars, black holes, and galaxies. If true, then perhaps every black hole in our universe is itself a seed for another cosmos, its singularity exploding outward as a white hole on the other side. In this grand view, our universe is not unique. It is one chapter in an endless cosmic library, each book opening with a Big Bang that is, in fact, a white hole exit from another story. And perhaps the deepest implication is this: what we call the beginning may not have been the beginning at all. It may simply have been a transition, a doorway, a bridge between realities. The Big Bang as a white hole reframes our existence not as a solitary cosmic event but as part of a vast network of connected universes, where death and birth are two sides of the same universal coin. The cyclic universe hypothesis is one of the most fascinating frameworks for rethinking the origin and destiny of everything we know. Instead of imagining the cosmos as a one-time event that began with the Big Bang and will either expand forever or collapse into oblivion, the cyclic model proposes that universes are born, evolve, and die in repeating sequences. In this view, the Big Bang was not the first moment of existence, but simply the latest in an eternal series of cosmic cycles. Now, how do white holes fit into this? One version of the cyclic model imagines that the collapse of one universe could naturally seed the birth of another. When a universe grows old, its stars burn out, galaxies collide, and eventually, much of its matter may end up swallowed by supermassive black holes. If black holes act not as endpoints but as gateways, then the collapse of matter into them could generate new universes on the other side, emerging as white holes. From within those new universes, the eruption of a white hole would look just like a Big Bang, a sudden expansion of space-time filled with matter and energy. This gives us a radical reinterpretation of cosmic life and death. Instead of thinking about universes as isolated bubbles that begin and end once, we can imagine them as links in an endless chain. One universe collapses, its black holes spawn white holes, and from those white holes new universes burst into existence. This cyclic picture resonates strongly with the symmetry built into Einstein's equations, where black holes and white holes mirror one another. Philosophically, this model has enormous appeal. It eliminates the need for a singular beginning of time. Instead of asking what happened before the Big Bang, we would recognize that the question itself is misplaced. The Big Bang was not a beginning, it was a continuation. Time extends backward infinitely, with universes arising, collapsing, and giving birth to new ones in a perpetual cycle. There is no first cause. The cosmos simply is, eternally recycling itself. There are multiple scientific approaches to cyclic models. One of the most famous is the Big Bounce hypothesis, which suggests that our universe expands until it reaches a critical point, then contracts under gravity into a big crunch, followed by a bounce into a new Big Bang. In some versions, this cycle repeats forever, with each iteration creating slightly different conditions, perhaps governed by the remnants of entropy and the information carried over from the previous universe. Other models tie into more exotic physics. For instance, loop quantum gravity proposes that quantum effects prevent space-time from collapsing into an infinite singularity. Instead, the collapse reaches a minimum size and then bounces outward again. If this is true, then the Big Bang itself may have been the rebound of a previous universe's collapse, a cosmic springboard rather than a true birth. White holes, in this picture, act as the mechanism for this rebound, converting the collapse of one universe into the expansion of another. But the cyclic universe hypothesis faces challenges. Entropy is one major problem. According to the second law of thermodynamics, entropy, the measure of disorder, always increases. If the universe cycles infinitely, entropy should accumulate across cycles, eventually preventing a new universe from forming in a low-entropy, highly ordered state like the one we see at our Big Bang. Some physicists have proposed clever solutions to this, such as the idea that each new cycle resets entropy, or that entropy drains into dimensions beyond our observable universe. But the puzzle remains open. Despite these challenges, the cyclic hypothesis continues to intrigue both scientists and philosophers. If the Big Bang was indeed a white hole, then the cyclic universe hypothesis becomes even more compelling. Every black hole in a dying universe could be a seed for the next, with its collapse feeding the birth of a white hole explosion. Our own Big Bang would then be just one cosmic rebirth among an infinite succession of them, and far from being the first white hole, it would simply be the latest. This perspective is both humbling and exhilarating. It suggests that our cosmos is not a unique miracle, but part of a grander, eternal rhythm. One universe collapsing into another, white holes giving birth where black holes once devoured. The cycle of creation and destruction is not only the story of stars and galaxies, but of universes themselves. The idea of a multiverse, that our universe is just one of many, has moved from the realm of science fiction into serious, if highly speculative, physics. Within this framework, the concept of the Big Bang as a white hole gains even more depth and intrigue. If our Big Bang was not a singular, isolated event but instead the outflow of energy from a black hole in some parent universe, then what we are really discussing is a mechanism for generating multiple universes. Each black hole could spawn a white hole, and each white hole could ignite a new cosmos. Suddenly, the multiverse is not just a wild guess, it becomes a natural consequence of the black hole-white hole connection. One way this works is through the so-called black hole cosmology hypothesis. Imagine that inside every black hole lies the seed of a new universe. To an observer in our universe, a black hole is a region of space-time that ends at a singularity. But to an observer inside that singularity, the collapse could bounce outward as a white hole, creating an expanding space-time bubble. That bubble would be cut off from our cosmos by the event horizon, making it invisible to us, but from within, it would appear self-contained, with its own laws of physics, constants, and possibly even dimensions. Our Big Bang, in this sense, was the opening of just such a bubble, one universe inside a larger multiverse. This neatly dovetails with eternal inflation theory, another major contender in multiverse discussions. Inflation refers to the brief period of rapid expansion right after the Big Bang, which helps explain why the universe appears flat and homogeneous. Some models suggest that inflation is not a one-time event but an eternal process. Space-time expands forever, spawning countless bubble universes along the way. Each bubble could have its own physics, like different values for the fundamental constants of nature. If so, then our Big Bang might simultaneously be interpreted as a white hole eruption and as one of these inflationary bubbles. The white hole Big Bang theory ties directly into this, because it provides a physical mechanism for how new universes can emerge. black holes in one region of spacetime generate white holes that seed entirely new expanding regions. In a sense, the multiverse becomes a vast cosmic tree, with black holes as the seeds and white holes as the sprouting universes, each branch growing into its own cosmos. Philosophically, the multiverse concept reshapes how we think about fine-tuning. Our universe seems strangely well suited for life. The constants of physics fall into narrow ranges that allow stars, planets, and biology to exist. Why should this be so? In a single universe picture, this fine-tuning looks suspiciously unlikely. But in a multiverse populated by countless universes, each with its own parameters, it is no surprise that at least one would have conditions favorable to life. From this perspective, our existence is not miraculous, it's statistical inevitability. The white hole model adds another twist to this. If universes are born through black holes, then the characteristics of the parent universe might influence the properties of the child universe. This has led to speculative ideas like cosmological natural selection, proposed by physicist Lee Smolin. He suggested that universes which produce more black holes might in turn generate more offspring universes, leading to a kind of evolutionary process across the multiverse. In this way, universes could evolve toward producing conditions that favor star formation, black hole creation, and eventually more universes. The Big Bang, as a white hole, is then not just an origin, it is part of a cosmic reproductive cycle. Of course, the multiverse remains highly speculative, and critics argue that it may be untestable, putting it outside the realm of science. By definition, we cannot directly observe other universes if they are causally disconnected from our own. Yet, proponents argue that indirect evidence, such as anomalies in the cosmic microwave background radiation, or the theoretical consistency of inflation and quantum gravity, might one day point us toward confirming or ruling out multiverse scenarios. The white hole Big Bang theory sits beautifully within this speculative framework. It suggests that our universe is not a lonely miracle but part of a grand tapestry of interconnected realities. Every black hole in our cosmos may be a portal to another universe, every white hole the birth cry of a new Big Bang. Our universe, in turn, may be just one node in an infinite multiverse, with no true beginning and no final end. And if this is the case, then the ultimate question becomes not why is there something rather than nothing, but which part of the multiverse do we inhabit, and how many other universes exist alongside ours? The Big Bang as a white hole is not just a reimagining of our cosmic origins, it is a doorway to the dizzying possibility that reality is far larger, stranger, and richer than we could ever have imagined. The cosmic microwave background, CMB, is often described as the oldest light in the universe, the faint afterglow of the Big Bang itself. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this faint radiation permeates the cosmos uniformly, with only tiny fluctuations. It is not only one of the most important pieces of evidence for the Big Bang theory, but also one of the most precise scientific datasets ever measured. If we want to test whether the Big Bang was a white hole, then the CMB is the first and best place to look for clues. The CMB is essentially a fossil of the universe when it was just 380,000 years old. At that point, the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was opaque. Light couldn't travel freely because photons were constantly scattering off charged particles. But once atoms formed, photons decoupled and began traveling freely through space. Those same photons have been journeying ever since, stretched by the expansion of space into the microwave frequencies we detect today. When we map the CMB, we're seeing a snapshot of the infant universe, like a baby picture of the cosmos itself. Now, what does the CMB tell us about the nature of the Big Bang? On the one hand, it confirms that the universe did indeed begin in a hot, dense state. The near uniformity of the CMB across the sky shows that the early cosmos was smooth and isotropic, while the tiny ripples, minute fluctuations in temperature, served as the seeds of galaxies and large-scale structure. This matches predictions of the Big Bang model almost perfectly. But what about the white hole hypothesis? Here the situation becomes more complicated. If the Big Bang were literally a white hole event, spewing matter and energy into space-time, we might expect the CMB to contain telltale signatures of that explosive outflow. Perhaps there would be directional asymmetries, shockwave patterns, or anomalies pointing to a localized eruption point. Yet, What we actually observe is astonishing uniformity. The CMB looks nearly the same in every direction, with no clear indication of a localized eruption. This suggests that the Big Bang was not the expansion of matter from a point in pre-existing space, but rather the expansion of space itself everywhere at once. This distinction is crucial. A white hole, as it is usually conceived, exists in a larger spacetime, ejecting matter into it. The Big Bang, however, was not an explosion into space, it was the expansion of space. The CMB strongly supports this interpretation. It shows a universe that inflated rapidly, smoothing out irregularities, rather than one that burst into a pre-existing arena from a single source. That said, the CMB does contain mysteries and anomalies that some speculative thinkers connect to exotic possibilities like white holes or multiverse interactions. For example, researchers have noted odd cold spots, unexpected alignments of fluctuations, sometimes called the axis of evil, and other irregularities that don't perfectly match the simplest inflationary models. While most cosmologists interpret these anomalies as statistical flukes or artifacts of measurement, some have suggested they could hint at collisions with other universes, or imprints of unusual physics at the very birth of our cosmos. If the Big Bang were indeed the outflow of a white hole, perhaps these subtle irregularities are the fingerprints of that process. Still, mainstream cosmology remains cautious. The overwhelming evidence from the CMB points to a universe governed by the Big Bang plus cosmic inflation, not a white hole eruption. Inflation, in particular, explains why the CMB is so smooth. It stretched out spacetime so rapidly in the first fraction of a second that any irregularities were iron flat. Without inflation, the CMB would look very different. In this sense, the CMB data is not just neutral about the white hole idea, it actively challenges it. A white hole eruption, unless it mimicked inflation exactly, would likely leave traces that we simply don't see. To put it another way, the CMB is the fingerprint of the Big Bang, but it is not the fingerprint of a white hole. It tells us the universe expanded, cooled, and evolved from an incredibly hot, dense state, but it does not reveal any evidence of matter spewing from a singular spacetime point as a white hole would. That doesn't mean the white hole idea is dead. It may be that the conditions at the Planck time, the first 10 to the power of -43 seconds of the universe, are hidden from us forever. The CMB only shows us what the universe looked like hundreds of thousands of years later. Whatever happened at the exact instant of the Big Bang is beyond the reach of current observations. It's possible that the white hole process, if it occurred, left no direct imprint we can measure today. In this sense, the CMB serves as both a confirmation and a limitation. It confirms the Big Bang as the correct description of the universe's hot, dense early state, but it also limits our ability to test speculative ideas like the white hole hypothesis. Unless we develop new ways of peering into the very first instant of cosmic history, the evidence for or against the Big Bang as white hole idea may remain forever out of reach. When we talk about black holes and white holes, it's easy to get caught up in their mathematical similarities and forget one of the most fundamental distinctions: scale. Black holes, as extreme as they are local phenomena within our universe. The Big Bang, by contrast, was a cosmic-wide event, the beginning of everything we know. This difference in scale is so vast that it complicates any simple one-to-one comparison between the two. Let's begin with black holes. Despite their terrifying reputation, black holes are not scattered everywhere in the universe. They are confined to specific regions, usually born from the collapse of massive stars or existing at the centers of galaxies as supermassive objects. They are localized distortions of spacetime, each with its own event horizon, its own gravitational well, and its own influence. Even supermassive black holes, billions of times more massive than the Sun, exist as individual points in space. They are powerful, yes, but they do not define the universe as a whole. You can think of them as cosmic sinkholes, local features within the vast landscape of spacetime. The Big Bang, however, was not a sinkhole but a cosmic origin. It did not occur at one location within space. Instead, it was the simultaneous expansion of spacetime everywhere. There was no center, no event horizon confining the event. Every point in today's universe was once compressed into that hot, dense primordial state. If you imagine rewinding cosmic history, every galaxy, every star, every atom collapses back into a single shared condition, the singularity-like state that we call the Big Bang. Unlike a black hole, which is a regional feature of spacetime, the Big Bang was a global event that defined the very structure of reality. This contrast is why physicists hesitate to equate the Big Bang directly with a white hole. A white hole, if it existed, would be a localized feature just like a black hole. It would sit in spacetime, ejecting matter outward but existing alongside other cosmic structures. The Big Bang, in contrast, wasn't an outburst into pre-existing space, it was the birth of space itself. When the universe expanded, it wasn't matter flying into empty surroundings, as with an explosion. It was space-time stretching, carrying galaxies and energy with it. The difference in scale is also tied to the difference in causal structure. Black holes influence their surroundings. They warp nearby spacetime, draw in matter, and shape their galactic environments. The Big Bang, however, set the rules for causality itself. It defined what near and far even mean. It established the boundaries of space and the flow of time. A white hole, in theory, could spit out matter into an already existing universe. But the Big Bang didn't happen inside anything. It created the very arena in which events can occur. Think of it like this. If black holes are local eddies in the river of spacetime, the Big Bang was the river's source, the spring from which everything flows. Comparing the two is illuminating in terms of their shared singularity-like mathematics, but it risks ignoring that one is a local disturbance and the other a cosmic genesis. And yet, the difference in scale doesn't make the white hole analogy meaningless, it just makes it more nuanced. Some theorists propose that perhaps the distinction between local and global is not as sharp as we think. If universes can be born inside black holes, then what appears local in one universe could be cosmic in another. From our perspective, black holes are just points scattered across space, but to an observer inside a hypothetical white hole spawned by one, that ejection event would feel like a Big Bang, a universe-scale eruption. This possibility blurs the distinction but also emphasizes why the scale question matters. The Big Bang wasn't just a burst of energy within a larger cosmos, it was everything. When we say the universe began, we're not describing one event among many but the single most universal event possible. If it was a white hole, it was not like any white hole theorized within our spacetime. It was a one-of-a-kind, universe-defining outflow unlike anything else. So, while the Big Bang and white holes share certain conceptual similarities, singularities, outward energy flow, time symmetry, the difference in scale sets them worlds apart. A black hole is a chapter in the cosmic story. The Big Bang is the book itself. When it comes to white holes, the concept doesn't just live in the realm of science fiction or casual analogy. It has been worked out in rigorous mathematical models by physicists trying to understand what Einstein's equations really allow. These models are essential, because while no one has ever observed a white hole, the mathematics of general relativity provides a testing ground for ideas about whether they could exist, how they might behave, and whether they could be connected to the Big Bang itself. The first and most famous mathematical description of white holes comes directly from the maximally extended Schwarzschild solution of Einstein's field equations. When Carl Schwarzschild solved these equations in 1916, his solution described a gravitational field around a spherically symmetric, non-rotating mass. That solution contained what we now recognize as a black hole, with an event horizon and a singularity at the center. But when extended mathematically to include all possible regions of spacetime implied by the equations, the solution also contained a second region, a white hole. This white hole region was essentially the time-reversed version of the black hole, where instead of everything being drawn in and never escaping, everything is expelled and nothing can enter. The problem, however, is that this eternal white hole in the Schwarzschild model is highly artificial. It doesn't form naturally from stellar collapse the way black holes do. It exists only in the fully extended mathematical solution, and it requires the entire spacetime to have been born with it already there. That makes it more of a mathematical curiosity than a physical prediction. Still, it was the first indication that general relativity doesn't forbid white holes. It allows them as mirror twins of black holes. Later researchers expanded on this. In the mid-20th century, John Wheeler and others began exploring the strange possibilities of Einstein's equations, including wormholes and Einstein-Rosen bridges that connected black hole regions to white hole regions. These bridges suggested that, at least mathematically, a black hole could be connected through spacetime to a white hole somewhere else, or even someone else. While these models generally collapse too quickly to be traversable, they opened up the tantalizing speculation that perhaps the Big Bang itself could be modeled as the white hole. End of such a bridge. More recently, physicists working on quantum gravity have revisited white hole models. Carlo Rovelli and Hal Haggard, for instance, have explored the idea that black holes might not end in singularities but instead undergo a quantum bounce, transforming into white holes. In their models, when a black hole collapses beyond the Planck density, quantum effects prevent the singularity from forming. Instead, the collapse reverses, and the black hole becomes a white hole that spews out its contents. In these scenarios, white holes are not eternal, but temporary phases of black holes. Rovelli has even suggested that this process could explain some mysteries of black hole evaporation and information loss. Mathematicians and physicists have also modeled the stability of white holes. Almost universally, the equations show that white holes would be unstable to even the tiniest perturbations. If any matter, even a single particle, were to interact with the white hole's event horizon, the solution breaks down and the white hole collapses. This fragility is one reason many physicists doubt their physical reality. But some models suggest that on a cosmic scale, such as the initial state of the universe, stability might not matter in the same way. If there was only one white hole, and it was the Big Bang, then its instability doesn't prevent it from existing. After all, it only needed to exist for an instant to seed the entire universe. There are also cosmological models that explicitly compare the Big Bang to white holes. Some researchers, working within general relativity and quantum cosmology, have built scenarios where the initial singularity behaves mathematically like a white hole singularity. In these models, the universe's expansion is essentially the outflow from that singular region, much like particles being expelled from a theoretical white hole. These models don't claim that the Big Bang was a white hole in the strict astrophysical sense, but they use the white hole analogy to describe the mathematics of cosmic expansion. Another mathematical avenue is through the study of Penrose diagrams, which are graphical representations of spacetime structures in relativity. When physicists draw the causal structure of spacetimes containing black holes, the mirrored white hole regions naturally appear. These diagrams show how time flows differently in black hole and white hole regions, reinforcing the idea that the Big Bang could be thought of as a one-time white hole event in terms of causal structure. So, while no white hole has ever been observed, the mathematics is robust. General relativity allows them, researchers from Schwarzschild to Rovelli have modeled them, and comparisons to cosmology have been drawn. The main question is whether these mathematical models describe physical reality, or whether they are beautiful but purely abstract solutions that nature never realized. The Big Bang as white hole hypothesis keeps the idea alive, because if we consider the Big Bang the ultimate one-time white hole, then perhaps the mathematics has already been realized, just not in the way early theorists imagined. One of the most persistent challenges with the white hole idea, and one of the biggest reasons many physicists remain skeptical about them, is the issue of stability. Even though white holes are permitted by Einstein's equations, just because something is mathematically possible does not mean it can survive in the physical universe. And when scientists test the stability of white holes using both general relativity and perturbation analysis, the verdict is overwhelmingly bleak. White holes are extraordinarily unstable. Let's begin with why. A black hole is stable in the sense that once its event horizon forms, nothing, not even light, can escape from inside it. If more matter or radiation approaches, it only strengthens the black hole, making it bigger. This is why black holes persist across cosmic timescales. They can survive for billions of years, quietly accreting material or waiting until Hawking radiation causes them to evaporate. Their very nature ensures their stability. Everything that touches them adds to their mass and deepens their gravitational well. White holes, by definition, are the time-reversed mirror of black holes. Instead of trapping matter forever, they eject matter forever. Instead of drawing in everything that crosses their event horizon, they forbid anything from crossing inward at all. But herein lies the instability. The moment you place a white hole in any real physical environment, its perfect no-entry condition is broken. If even the tiniest particle of dust, a photon, or any disturbance from the outside universe interacts with the white hole's boundary, the mathematical solution collapses. Essentially, the white hole can't tolerate any imperfection in its surroundings. Yet our universe is full of imperfections, from stray particles to background radiation. Think of it like balancing a pencil perfectly upright on its tip. In theory, It can stand there indefinitely. But in practice, the tiniest vibration, the smallest puff of air, or even a microscopic irregularity in the pencil itself will cause it to topple. A white hole is the cosmic equivalent of that precarious pencil, mathematically possible, but physically unachievable under real-world conditions. This instability makes white holes vastly different from the Big Bang. The expansion of the universe has been remarkably stable. Once cosmic inflation ended, the universe continued expanding in a predictable way, cooling, forming galaxies, stars, and planets. Today, 13.8 billion years later, that expansion is still ongoing, and even accelerating due to dark energy. If the Big Bang were truly identical to a white hole, we might expect instability and collapse, but that's not what we see. Instead, we see a universe that has endured and evolved. Some theorists have attempted to salvage the concept by introducing modifications. For example, in quantum gravity models like those proposed by Carlo Rovelli and Hal Haggard, white holes emerge not as eternal objects but as brief transitional states, the bounce phase when a collapsing black hole avoids singularity and reverses into expansion. In such scenarios, the instability is less of a problem because the white hole isn't expected to last forever. It only needs to exist long enough to release information or matter. But even here, the white hole isn't a stable, standalone cosmic object. It's more like a fleeting bridge in a longer process. Another point often raised in cosmological discussions is that if the Big Bang was a white hole, its instability might not matter in the traditional sense. The Big Bang did not occur inside a larger spacetime full of perturbations. It was the origin of spacetime itself. There were no stray particles floating nearby to collapse it, because there was no outside environment to disturb it. In this one-time, universe-scale context, the usual stability issues may not apply. What would be impossible for a localized white hole within an existing universe might still make sense when describing the birth of a universe itself. However, this raises another problem. If white holes only work as one-off cosmic events, then they cannot be a general feature of relativity, but rather a metaphorical way of describing the Big Bang. That makes them far less compelling as physical predictions. After all, part of what makes black holes scientifically valuable is their ubiquity. They are not rare. They are expected products of stellar collapse and galactic evolution. White holes, on the other hand, would be freak one-time phenomena, with no evidence of recurrence. So, in summary, the stability issue is one of the main reasons why mainstream physics doesn't accept white holes as real objects populating the cosmos. They collapse too easily, they cannot form naturally in astrophysical processes, and they don't match the observed endurance of our universe's expansion. Yet, the fact that the Big Bang itself is stable, and yet shares some conceptual features with a white hole, keeps the analogy alive. If the Big Bang was indeed a white hole, it was not a typical white hole but a unique, universe-scale exception, unlike anything Einstein's equations normally describe. The idea of the white hole Big Bang gains much of its appeal from the image of a sudden, explosive release of energy and matter filling the cosmos. At first glance, this sounds very much like what happened in the earliest moments of our universe. But modern cosmology has given us a more precise explanation for that rapid, early expansion, one that does not require invoking white holes. This explanation is known as cosmic inflation. Inflation theory was first proposed in the early 1980s by physicist Alan Guth, later refined by others like Andrei Linde, Alexei Starobinsky, and Paul Stenhardt. The central idea is that in the earliest fraction of a second after the Big Bang, between about 10 cubed and 10 cubed squared seconds, the universe underwent an astonishing period of accelerated expansion. Space itself grew exponentially, doubling in size again and again in less time than it takes light to cross a proton. By the end of inflation, the universe had grown unimaginably larger than it had been at the start. Why was inflation introduced? Because the simple Big Bang model, without inflation, leaves some puzzles unexplained. For instance, at the horizon problem, the universe looks remarkably uniform in every direction, especially in the cosmic microwave background radiation. But without inflation, regions far apart in the sky would never have had time to exchange information or energy to become so uniform. Inflation solves this by stretching a once-connected, tiny patch of space to cosmic scales. At the flatness problem, the universe appears geometrically flat, meaning the density of matter and energy is extremely close to a critical value. Without inflation, This balance would be incredibly unlikely. Inflation naturally drives the universe toward flatness, just as blowing up a balloon makes its surface appear flatter the larger it gets. At the monopole problem, certain particle physics theories predict heavy relics like magnetic monopoles, but we don't observe them. Inflation dilutes their abundance to near zero, explaining why they are absent. So inflation wasn't proposed just to explain rapid growth, but to resolve deep inconsistencies in cosmology. And the beauty is that inflation matches observations. The tiny quantum fluctuations that occurred during inflation were stretched into macroscopic density variations, which later seeded galaxies and large-scale cosmic structures. When we look at the cosmic microwave background, CMB, today, its faint patterns match what inflation predicts, a nearly scale-invariant spectrum of fluctuations. Now, how does this relate to the white hole idea? On the surface, both describe sudden expansion. A white hole, if it existed, would spew out matter and energy all at once, with no way of containing it. Inflation, by contrast, is a process driven by a hypothetical energy field, often called the inflaton field, which dominated the early universe. Instead of being a spontaneous, unstable eruption like a white hole, inflation is a controlled, calculable mechanism that naturally ends after a brief but significant phase, transitioning into the hot Big Bang that followed. Another important distinction is that inflation explains why the expansion was not only rapid but also stable and enduring. White holes, as we've discussed, are notoriously unstable. A single disturbance could collapse them. Inflation, however, fits smoothly into the laws of quantum field theory and general relativity. It provides a framework in which the universe can expand rapidly and then continue expanding in a more moderate way, leading to the cosmos we observe today. Furthermore, inflation does not require an external trigger. In the white hole analogy, we might ask, what caused the white hole to appear? But inflation begins naturally if certain conditions in the early vacuum state are met. In some models, inflation could even be eternal, meaning that while inflation ended in our region of space, other regions are still inflating, leading to the multiverse hypothesis. In this light, inflation effectively removes the need to think of the Big Bang as a white hole. It gives us a well-tested, mathematically consistent explanation for why the early universe expanded so quickly, why it looks the way it does today, and how galaxies and clusters formed. White holes remain speculative with no observational evidence, while inflation has strong indirect support from the CMB and large-scale structure surveys. That said, some cosmologists keep the comparison alive because inflation, while powerful, still doesn't answer everything. For example, it doesn't tell us exactly what the inflaton field is, or why it had the properties it did. In that sense, white holes and inflation occupy different roles in cosmological thought. Inflation is the working theory supported by data, while white holes are the exotic, what-if scenario that forces us to think about time symmetry, singularities, and the possibility of hidden connections to other universes. So, if someone asks, was the Big Bang a white hole? The best answer from modern science is, no, it was inflation. Inflation gave us the rapid early expansion we associate with a white hole eruption, but it did so within a stable, predictive framework that still governs cosmology today. The white hole analogy may still inspire philosophical reflection, but inflation remains the scientific explanation that fits the evidence. When we talk about the strange connections between black holes and white holes, one of the most intriguing bridges between the two ideas comes from Stephen Hawking's groundbreaking discovery in the 1970s. Black holes are not truly eternal. Instead, through a subtle quantum process, they emit radiation and can eventually evaporate. This phenomenon, known as Hawking radiation, has reshaped how we think about black holes and even raised questions about whether their ultimate fate could mimic white hole-like behavior. To appreciate the link, let's first unpack what Hawking radiation actually is. In classical general relativity, a black hole is absolute. Nothing escapes once it crosses the event horizon. But Hawking showed that when you take quantum mechanics into account, the story changes. Near the event horizon, the fabric of spacetime is never completely empty. Instead, it is buzzing with quantum fluctuations, particles and antiparticles constantly appearing and annihilating in pairs. Normally, these fluctuations cancel each other out almost instantly. But near a black hole's horizon, one particle in the pair can fall into the hole while the other escapes into space. To an outside observer, It looks as if the black hole is radiating particles. This radiation comes at a cost. The black hole loses a tiny amount of mass with each emission. Over an incomprehensibly long period of time, far longer than the current age of the universe for stellar or supermassive black holes, a black hole would shrink and eventually evaporate entirely. Now here's where things get interesting. What happens at the final stage of this evaporation? Some physicists have speculated that when a black hole reaches its quantum limits, when it can no longer shrink without confronting the unknown rules of quantum gravity, it might undergo a transformation, releasing its remaining contents in a sudden outburst. This process could resemble a white hole explosion, where instead of swallowing matter forever, the black hole spits everything back out. In fact, a few theoretical models suggest that black holes may not die quietly at all. They might transition into small, short-lived white hole remnants in their final moments. In this scenario, the black hole essentially reverses its role. Instead of trapping information, it releases it. The evaporation process would then end not with a whimper, but with a burst that has white hole-like qualities. Carlo Rovelli and Francesca Vidotto, two prominent researchers in quantum gravity, have explored this very possibility. Within the framework of loop quantum gravity, they propose that a black hole could bounce instead of collapsing into a singularity. At first, it behaves like a black hole, absorbing everything. But after an extremely long time, quantum effects cause it to rebound, re-emerging as a white hole that ejects the information and matter it once consumed. In a sense, the black hole's evaporation becomes the seed of a white hole's birth. This idea is deeply connected to the information paradox, the puzzle of whether information that falls into a black hole is truly lost forever. Hawking radiation itself, as originally conceived, seems to carry no information about the matter that formed the black hole. If black holes completely evaporate without releasing that information, it would violate the laws of quantum mechanics, which insist that information cannot be destroyed. But if evaporation leads to a white hole phase, then the information could, in principle, be released back into the universe, preserving the symmetry of physics. Of course, we must emphasize that this is still speculative. No one has ever observed Hawking radiation directly. It is far too faint to detect from astrophysical black holes with our current technology. And the final stages of black hole evaporation are so far in the future for most black holes that we cannot test them observationally. Still, the mathematics of quantum gravity provides a playground for these ideas, and they remain among the most fascinating attempts to reconcile relativity and quantum mechanics. The connection to the Big Bang is tantalizing. If black hole evaporation ends in a white hole, like release, could the birth of our universe have been the ultimate version of such a process? Some theorists speculate that perhaps a black hole in a parent universe evaporated, and instead of disappearing into nothingness, it gave birth to our Big Bang. In this way, Hawking radiation and black hole evaporation may not just explain how black holes end, but how universes begin. In summary, Hawking's discovery showed us that black holes are not the cosmic prisons they were once thought to be. Their evaporation opens the door to new possibilities, that death and birth in the cosmos might be more connected than we ever imagined. And while the idea that a black hole's final breath could look like a white hole eruption is still unproven, it offers one of the most elegant and poetic bridges between two of physics' strangest predictions. The black hole information paradox is one of the deepest mysteries in modern physics, and it lies right at the crossroads of quantum mechanics, general relativity, and cosmology. If we want to understand whether white holes could play a role in resolving this paradox, we need to carefully unravel what the paradox is, why it challenges the very foundations of science, and how the concept of a white hole might offer a potential, though still highly speculative, solution. At its core, the paradox arises because black holes appear to destroy information. In physics, information doesn't mean casual facts or data in the everyday sense. It refers to the complete physical description of a system, the arrangement of particles, their energies, spins, and so forth. According to quantum mechanics, this information should never be lost. Even if systems change, decay, or evolve, the information is always preserved in principle, though it may become inaccessible in practice. This principle is called unitarity, and it is one of the bedrocks of quantum theory. But black holes challenge this rule. When matter falls into a black hole, all of its unique information seems to be swallowed. Outside observers can only measure three basic properties of the black hole: its mass, charge, and spin, leading to the famous phrase coined by physicist John Wheeler, black holes have no hair. Everything else, no matter how complex the original system, vanishes from our universe's perspective. Then Hawking's discovery of black hole evaporation made the paradox worse. If black holes eventually evaporate away through Hawking radiation, what happens to the information they contained? Hawking radiation appears to be thermal, random, featureless, carrying no trace of the details about the material that fell in. If the black hole disappears completely, and the information never emerges, then the laws of quantum mechanics would be violated. This is the paradox. General relativity says the information is lost, while quantum mechanics says it cannot be. Now, where do white holes enter the picture? Some theorists suggest that black holes and white holes could be two phases of the same process. A black hole swallows matter and information, but instead of being destroyed forever, that information could reappear later through a white hole. In this way, the paradox could be resolved. The information is not lost, it's just delayed, hidden, or transformed. Imagine this sequence. A star collapses into a black hole, information gets trapped inside, the black hole ages and evaporates, and then, instead of vanishing, it transitions into a white hole. The white hole then ejects the stored information back into the universe. From our perspective, it might take billions or even trillions of years, but the information would eventually return. In this model, the black hole's interior acts like a vault, and the white hole serves as the vault's exit door. This idea has been explored in the context of loop quantum gravity, where space-time itself is thought to be quantized. In such models, a black hole might not collapse to a true singularity but instead bounce into a white hole. The bounce would allow information to escape, preserving unitarity. Some physicists, like Carlo Rovelli, have gone further to propose that the white hole might even be tiny and stable, acting as a long-term storage of information until it gradually releases it. Of course, this raises other questions. If black holes transition into white holes, why haven't we observed any? The answer might be that the timescales are unimaginably vast. For a stellar mass black hole, the evaporation time through Hawking radiation is about 10 years, far longer than the current age of the universe. For supermassive black holes, it's even longer, around 10 to the power of 1 years. If white holes only appear at the very end of this process, we simply haven't lived long enough to see one. Another angle is that information might already be encoded in Hawking radiation itself in a very subtle way, a possibility supported by developments in string theory and the ADS-CFT correspondence. In this case, the radiation carries hidden correlations that preserve information, and white holes wouldn't be necessary. Yet some physicists argue that the idea of a white hole end phase provides an elegant, time-symmetric answer that ties neatly into the broader question of whether our universe itself could have emerged from a similar bounce. Philosophically, the connection is compelling. Black holes seem to erase history, while white holes seem to create it. If they are two sides of the same coin, then the paradox may dissolve, replaced by a larger symmetry in nature. Instead of destruction and creation being separate, they might simply be different perspectives on one unified process. Still, it's important to emphasize, this remains unproven. White holes are entirely theoretical, and no observational evidence exists for them. The information paradox itself is still unsolved, despite decades of work. But the white hole idea persists because it offers a vision of cosmic justice, where the universe doesn't simply allow information to vanish into nothingness. Instead, it hides and releases it, ensuring that the grand book of the cosmos never loses a page. In the end, whether or not white holes truly resolve the paradox, they remind us of an important truth. We are standing at the frontier of knowledge, staring into the deep mysteries where quantum mechanics and gravity collide. And in that space, even the wildest ideas, like white holes restoring lost information, demand our attention. When we step back from the equations and the technical debates for a moment, the question of whether the Big Bang was a white hole takes on a much broader dimension, a philosophical angle that reaches beyond pure physics. It invites us to ask not just what the universe is, but how we should think about it. Is labeling the Big Bang as a white hole a literal scientific proposition? Or is it, perhaps, more of a metaphor, an evocative way of framing an event so far outside our everyday experience that language itself struggles to capture it? Philosophy and cosmology have always been intertwined. The earliest thinkers, from ancient Greek philosophers to Indian and Chinese cosmologists, weren't just trying to describe the mechanics of the universe. They were grappling with the deeper meaning of existence, creation, and time. Today, physics gives us extraordinary mathematical tools, but we still face the same dilemma. When we push to the very edges of knowledge, the Planck time at the birth of the cosmos, or the singularity inside a black hole, our words become stretched, our concepts blur, and metaphor often fills the gaps where precise understanding cannot yet reach. Calling the Big Bang a white hole could fall into this category. On the one hand, the comparison makes sense. Both involve matter and energy flowing out from a singular point, both defy the normal rules of entry and exit, and both stand as time-reversed mirrors of black holes. The symmetry is elegant. It makes the universe feel like it's built on a kind of poetic logic, collapse balanced by eruption, consumption paired with release. In this light, the Big Bang as a white hole is a way of making sense of the incomprehensible. But on the other hand, science demands caution. A metaphor, no matter how appealing, can be misleading if we start to treat it as literal truth without evidence. A white hole, as predicted by Einstein's field equations, is a very specific object with a very specific space-time geometry. It is embedded within a particular mathematical framework, complete with its own event horizon and causality rules. The Big Bang, by contrast, is not localized in space but everywhere at once. It is the expansion of space-time itself, not an object sitting within space-time. In this sense, calling the Big Bang a white hole might be more poetic than physical, a way to describe its explosive qualities without implying that it follows the exact rules of white hole physics. Yet, philosophy urges us not to dismiss metaphors so quickly. Throughout history, metaphors have often been stepping stones to new discoveries. Think of how Newton described gravity as a force pulling apples to the ground, a metaphor that eventually evolved into Einstein's picture of warped space-time. Think of how physicists speak about particles as waves or clouds of probability. These are not literal descriptions, but they are powerful models that guide understanding. So perhaps calling the Big Bang a white hole is not wrong. It may be an intermediate way of thinking, a mental model that helps us conceptualize something that lies beyond our current mathematical and experimental reach. There's also a deeper philosophical implication here, the unity of opposites. Black holes and white holes, if they exist, are mirror images in time. Creation and destruction, inflow and outflow, are part of the same whole. If the Big Bang really were a white hole, or at least behaves like one, it would suggest that the universe itself embodies this symmetry of opposites. It would mean that our cosmos is not an exception, but part of a larger cycle where everything swallowed is eventually released, everything hidden is eventually revealed. This resonates with ancient philosophical traditions as well as modern physics, suggesting that the universe is not chaotic or arbitrary but structured by balance. But philosophy also allows us to entertain another possibility. Maybe the question itself is flawed. Maybe the Big Bang is not a white hole, not even metaphorically. Maybe it's something so radically different that even comparing it to known concepts is misleading. In this view, attaching the white hole label could be more of a psychological comfort than a physical insight. It gives us a handle on something we can't fully grasp, but it might distract us from imagining entirely new categories of phenomena. After all, if the universe emerged from something stranger than any white hole, clinging to the metaphor could actually limit our thinking. And so, we arrive at a tension. The Big Bang as a white hole is at once an illuminating metaphor and a potential physical idea, but it may also be neither. Its real value might lie in the questions it provokes rather than the answers it provides. By asking the question, is the Big Bang a white hole? We force ourselves to confront the boundaries of science and language. We admit that some mysteries are so profound they require both physics and philosophy to even begin approaching them. In the end, perhaps the best way to view this is not as an either-or but as a both-and situation. The Big Bang as a white hole may indeed be a metaphor, a way of imagining cosmic creation. But it could also point, however faintly, toward a deeper truth that science has not yet fully uncovered. Philosophy reminds us that metaphors are not the destination, but sometimes they are the road that leads us closer to reality. When we shift into the territory of scientific skepticism, the conversation around white holes, and specifically, whether the Big Bang could have been one, takes on a different flavor. Up until now, we've explored the poetic symmetries, the theoretical physics, and the tantalizing possibilities. But science as a discipline rests not on elegance or metaphor but on evidence. And this is precisely where the white hole hypothesis runs into its greatest challenge. The mainstream scientific position is fairly clear. White holes are speculative, and there is no observational evidence that they exist. Black holes, in contrast, have gone from being purely mathematical predictions of general relativity to observable astrophysical realities. We've detected their gravitational pull on nearby stars, we've heard the ripples of spacetime from black hole mergers via gravitational waves, and we've even imaged the shadows of supermassive black holes through the Event Horizon Telescope. Black holes are not just theoretical constructs, they are confirmed members of the cosmic zoo. White holes, however, have never been observed. Not once. No astronomical event has been conclusively identified as a white hole. No burst of matter has been traced back to an event horizon that repels everything instead of absorbing it. The absence of evidence doesn't mean they are impossible, but it does mean they occupy a very different status in physics, a mathematical possibility rather than an empirical reality. Skepticism arises for several reasons. First, the equations of general relativity that allow for white hole solutions also predict that such objects would be highly unstable. The smallest disturbance, like stray particles or radiation from the surrounding universe, would destabilize a white hole almost instantly, causing it to collapse. In other words, even if white holes could form, they wouldn't last long enough for us to notice them. This makes the idea of a universe-spanning, stable white hole, like the Big Bang, sound even less plausible in the eyes of many scientists. Second, mainstream cosmology already has robust models to explain the features of the Big Bang without invoking white holes. The standard cosmological model combined with inflation theory accounts for the universe's rapid expansion, the distribution of galaxies, and the cosmic microwave background radiation. These models have been tested against observations and have consistently held up. By contrast, the white hole hypothesis lacks comparable predictive power and hasn't been integrated into a model that explains existing data in a way that rivals inflationary cosmology. Third, skepticism is strengthened by the principle of Occam's razor, the idea that, all else being equal, the simplest explanation that accounts for the data should be preferred. If inflation and standard cosmology explain the observable universe without requiring white holes, then adding white holes to the picture seems unnecessary. This doesn't mean the idea is wrong, but in science, additional hypotheses must earn their place by providing explanatory or predictive power beyond what existing theories can already do. So far, the Big Bang as a white hole has not cleared that bar. But scientific skepticism is not cynicism, it's a disciplined demand for evidence and clarity. Many scientists remain open-minded about the possibility that new discoveries in quantum gravity or high-energy astrophysics could shift the picture. If, for example, we discovered signatures in the cosmic microwave background or observed astrophysical phenomena that could only be explained by white holes, the mainstream position would adapt. Skepticism in science is never permanent refusal, it's provisional doubt, waiting for data. It's also worth noting that historically, many phenomena now central to physics were once speculative. Black holes themselves were dismissed for decades as mathematical curiosities before observational breakthroughs changed that view. Gravitational waves were long considered undetectable, and yet LIGO proved otherwise. Even the expanding universe was resisted at first by scientists who preferred a steady-state cosmos. Skepticism is a safeguard, not a death sentence. It ensures that only the strongest ideas survive. From this perspective, the mainstream position on white holes reflects the healthy caution of science. Without evidence, they remain beautiful but unproven ideas. The Big Bang as white hole analogy might inspire thought experiments and fuel philosophical debate, but until it makes testable predictions and gains empirical support, it will stay outside the core of cosmology. That doesn't make the idea meaningless, it makes it a fringe hypothesis waiting either to be falsified or to be vindicated. Science is full of such edges, where speculation dances just beyond the border of knowledge. For now, though, the skepticism is justified. White holes are not part of the established scientific picture of the universe. They are fascinating, elegant, and evocative, but speculative nonetheless. Even though white holes remain speculative and lack empirical support, the idea persists, and not just in the margins of theoretical physics, but in the imaginations of scientists, philosophers, and curious thinkers alike. Why does it remain so compelling, despite the skepticism? The answer lies in something deeper than evidence. It lies in the human fascination with symmetry, balance, and completeness in the universe. At its heart, The white hole concept offers a kind of cosmic neatness. Black holes, which we know exist, are objects of profound asymmetry. They are points of no return. Matter and information flow in but never come out. If you imagine the universe as governed by fundamental laws that are time-symmetric, then having only black holes without their time-reversed counterparts feels incomplete, almost like reading only half of a sentence. White holes, as theoretical opposites, restore that balance. They provide an elegant mirror image, objects where everything comes out but nothing goes in. This aesthetic appeal of symmetry has always been a driving force in science. Symmetry underlies Einstein's relativity, quantum mechanics, and the standard model of particle physics. Time reversal symmetry, charge parity symmetry, and gauge symmetries have guided physicists to discover deeper truths. So when the math of relativity naturally suggests that white holes should exist, it resonates with this long tradition of symmetry leading to insight. Even if unobserved, they feel like they belong in the cosmic story. Another reason the idea lingers is the mystery of beginnings. The Big Bang is the ultimate origin point for our universe, and yet it resists intuitive understanding. Saying that the Big Bang was a white hole provides a narrative that feels more accessible. It's not just an unexplained eruption, but the other half of something familiar. For those grappling with the sheer strangeness of creation ex nihilo, the white hole framework gives a way to picture it. It transforms the question, where did the universe come from, into where did the white hole come from? Which may not be an answer, but at least reframes the mystery in terms of known physics. The persistence of the idea also ties to the desire for completeness in cosmology. Black holes raise troubling paradoxes, like the information loss problem. If matter disappears into a black hole forever, does information get destroyed? This clashes with the fundamental principles of quantum mechanics. White holes offer a tantalizing escape hatch. Maybe black holes aren't the end of information, but gateways that eventually release it back into reality. In this sense, white holes are not just a symmetry to black holes, but a potential resolution to some of physics' deepest puzzles. Culturally, the concept of white holes also captures the imagination. They embody a kind of cosmic generosity, a source rather than a sink, a fountain instead of a drain. In a universe often dominated by destruction and collapse, supernovae, black holes, entropy, white holes represent the opposite force: creation, release, and expansion. That duality resonates not only with physics but with myth, storytelling, and human psychology. Just as many cultures throughout history have envisioned cycles of death and rebirth, consumption and creation, black holes and white holes embody that archetypal rhythm at a cosmic scale. Another factor is the role of speculation in science itself. Scientists are often motivated not only by data but by the questions that inspire them to look for data. White holes persist because they are intellectually provocative. They challenge the boundaries of what we know, they ask what if, and they provide a framework for imagining what might lie beyond our current observational limits. Even if the Big Bang wasn't literally a white hole, the idea pushes cosmologists to refine models of singularities, space-time, and quantum gravity. In this way, the persistence of the idea is less about literal belief and more about its utility as a thought experiment. Finally, the idea endures because it gives the universe a sense of cohesion and beauty. Humans are naturally drawn to patterns. We don't just want the universe to exist, we want it to make sense, to have balance, to reflect an underlying order. White holes provide that order, pairing with black holes in a cosmic dance of opposites. They suggest that the universe may not be a random accident but part of a deeper design, whether natural or metaphysical. So even as mainstream science views white holes with skepticism, the idea persists because it satisfies something profound in both the scientific and human spirit. It gives symmetry where otherwise there is imbalance, narrative where otherwise there is confusion, and hope for resolution where otherwise there are paradoxes. In short, it remains compelling not because it is proven, but because it makes the universe feel more whole. As we arrive at the closing reflection, we stand at the crossroads of science, philosophy, and imagination. Over the course of this journey, we've asked whether the Big Bang, that primordial eruption of space, time, matter, and energy, might not simply have been a mysterious beginning, but instead the ultimate example of a white hole. We've explored definitions, contrasts, equations, paradoxes, and even the boundaries of speculation, tracing the threads of this mind-bending question. But now, as we pull back from the technical details, we're left with something bigger, a sense of awe at the mystery of origins. If black holes are the devourers of the cosmos, silent prisons where matter vanishes beyond event horizons, then white holes, at least in theory, are the fountains of creation, flinging matter outward with no possibility of return. To ask whether the Big Bang was itself a white hole is to place our universe in that narrative of symmetry and balance, a grand story where every sink has a source, every collapse has an outburst, and every end is mirrored by a beginning. And yet, the more we've uncovered, the more we've realized that the answer isn't simple. Maybe the Big Bang does look like a white hole in its behavior, an unstoppable expansion, a one-way release of matter and energy. Maybe the equations of general relativity really do whisper about this symmetry, hinting that white holes ought to exist. But at the same time, the evidence is missing. The mathematics is incomplete. The physics of singularities and quantum gravity remains unresolved. So we are left with possibilities. Perhaps the Big Bang was the one and only white hole, a once-in-eternity event that unleashed an entire universe and will never be repeated. Perhaps it was the outflow of a black hole in another cosmos, making our universe the child of another's collapse. Or perhaps it wasn't a white hole at all, but something even stranger, something our current science can't yet name or even imagine. This, in many ways, is the beauty of the question. Science thrives on the tension between what we know and what we can only guess at. The Big Bang, whether or not it was a white hole, is still the greatest scientific mystery of all. A horizon we cannot see past, a door locked from the other side. And asking these kinds of questions, wild, bold, imaginative, keeps us moving forward, reaching for the next insight, the next observation, the next theory that might illuminate the darkness. So as we close, let me leave you with this thought. Was the Big Bang the ultimate white hole? Or is it something beyond even that, a phenomenon so alien, so profound, that our current physics is only scratching the surface? One day, future generations may look back at our guesses and smile at how close, or how far, we were. Until then, the mystery remains open, inviting us to wonder, to question, and to dream. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.